This is AUTOMAT Live-Coding, and today we are going to continue working on our assembler environment. The plan for today is to do those two tasks. So first, we have a nice library of instructions that we've done last time. Today, we'll actually make it possible to pull instructions out of this library. Yeah, something very basic, something that should have been there maybe for a long time. And that's going to be easy. Like, the main thing is that we would like to create a sort of drag and drop for instructions so that they can be chained together. So that we can create basic blocks, kind of. So a basic block essentially is a sequence of instructions with no jumps in the middle. So nobody can jump into a basic block. It's just executed consecutively until the end. And at the end it has a jump instruction, an instruction which redirects the basic flow elsewhere. I don't see any pictures here. Let's check images. This is pretty much what is basic block. They are visualized in various ways. They're often used in decompiling, I think. So here is an example of a program which is decompiled into basic blocks. So there is quite a lot of them here, because most functions, real functions, are rather large, rather complex. We are not going to do anything like that. Our basic blocks are going to be closer to this. Okay, let's start by pulling the instruction out, and then we will have to actually make a pause and do some design. So let's do the easy stuff first. Those instructions, they may look slightly differently than last time. This is because I took the liberty and implemented some of the to-dos yesterday. So long lines on instructions now have new lines inside, so not all of the text is on a single line. Nice, right? The instructions are also ordered in a nicer way. So for instance, now when I switch, I have this instruction which does the 9-bit rotate with immediate. And this is like the same instruction, but with a slightly larger operand. So we have a block of all of those instructions with larger and larger operands, and then we have a different instruction, again, with larger and larger operands. So it's easier to find the instruction you are looking for now, because they are ordered in a slightly nicer way. Okay. Then we also have this feature, so it's a typography trick, which is actually not used by digital typography almost at all. But generally, when you have a piece of text, you can, and if you want to make it like flow nicely, the text that we have is actually not super well balanced. I tried to divide them more semantically than typographically. But the idea here is, if you want to make text fit some like fixed width column, you can actually stretch it a little bit. So this text here, you can see that it's slightly stretched, and this one is slightly squeezed. It happens only sometimes, but it makes it, I think, easier to read. Like, maybe not easier to read. It improves the balance, like the visual balance of text on the card. Then, yeah. Oh, and when we have fixed registers, sometimes it's the case, for example, when we add stuff, maybe not. Signed math, yeah, signed math has plenty of those. So when a register can be changed when it's when it's an operand of an instruction, we show it in normal colors. But when it's fixed, we show it in this icy blue tint. Okay, so those are some small updates that happened off stream. I also wrote down some of the to-dos that I don't think we'll certainly not have the time to do. Those are like quality of life fixes and just straight bug fixes that we should take care of. Yeah, I could probably divide this into like priority categories. We're not going to worry about those. Today we are just making sure we serialize the instructions. Okay, I think we'll have to take a look at the find action method. So if we are pressing with the left mouse button, okay, so here we should check if the pointer, if this contact point, lies on the middle card. There are two ways to do this. Let me mess this up. Okay. One of them would check the rectangle which we usually reserve for the front card. I think this is probably what we should do. Because sometimes the Z order is broken, but I think this Z order, we should just fix it elsewhere. So that we could probably just assume that the front card is horizontal in the front. Yeah, and we need to implement pictures for missing flags. Let me add this up. Generally speaking, I think signed math needs some design. Okay, so we have some const expr variables here. But we also have this like instruction rect, an instruction around the direct. I think we should rename this to make 0. I think we could also remove a lot of them. When I'm looking at how we do some things, I think we are... So this is not like super complex, but I feel a lot of the complexity here could be removed if we had access to like nicer features. In Rust, some of the things would be just so nicer to write, so much nicer to write. Okay, I will move this variable here. Let's fix all of them. Okay, now we can rename this to K-rect. I'm mixing the version with prefixes and without. I don't think I need them everywhere. Now, I've done this because now we can actually use this rectangle object, and it's going to make this a little bit easier for us. think there is a function move by. Mark this as const. Cool. I don't like the fact that we have a mix of functions which return a copy and functions which mutate in place. I think if we used past tense, maybe we could use that to distinguish between them. And we have no discards, so that protects us. I think I can even take this and assign it to some const exp. I will make it static because I don't really need to link it anywhere. I mean, it can be eliminated from the final binary. We can check if this works by clicking the front of the deck. Nothing happens. Cool. I will also update the pointer move, this one. Cool. It was so annoying actually to have these constantly twisted. Okay, another interesting thing. Incrementing 8-bit register is actually shorter than 16-bit register. But 32 is also just 2 bytes. So 64 and 16 they require more bytes. The more you know. Okay, so now we want to do something here. We want to create this new card. Let's look at how we create new objects. I guess toolbar is used to create new objects, right? Okay. It seems like this is the code that we could just copy and paste here. Okay, this hover is just a pointer to the widget which is currently hovered. Since we are only using this to populate scale, we don't quite need it. And this we already have, this is the contact point variable. So we need to call this create and give it some prototype. Do we have any prototypes for the instruction? I need to call fix parents here. I think this section is the same between those two. We could probably merge this. Anyway. Okay. The card is going to be in the wrong position, but should work. Yeah. Contact point is going to be equal to our contact point minus this. Yeah, it works. Let's, for example, take the increment instruction on, I didn't mean that, 64-bit register or 8-bit register. 8-bit actually is fine. Then we could multiply it by 2. Now we have 2. Now we have 4. Now we have 8. Nine, 10. Yeah. So there is a small issue with those cards, is that they are not aligned with the metric system. So they have a small gap. We have to fix this. We will just round their size. So here is an example program that sets the value of some register to 10. Oh, actually it sets the value of the AX register. That's not what I want. What I actually wanted was to set the CX register. Now we have 2 here. Now we have 8. It's a very funny way to set the value of a register. So now the CX register is at 10. For instance, if I wanted to execute something 10 times, just for an example. So actually, like the right way to do this would be to obviously use the move instruction to initialize it to 10. But if we don't have move instruction, this is how we have to do it. So now So the proper way to do a loop would be to do a test here and jump out, but we are guaranteed to have some value in the register, so we don't need to do that. Okay, so that would be initialization would be 1. And this card would be a second basic block. Let's imagine there is a connection from here going here. Actually, no, it should be part of the same kind of tape. So this block, so every card should have some kind of connection at the bottom, something that allows me to choose what happens next once it finishes. And those loops, they will actually have to because they will have a normal continuation connection, and they will also have the side jump. Actually, let me double check the loop instruction. So we also need a regular jump. Something like this here. So we have our initialization, which then jumps here. This would go into some extra object, for example, like some macro or a timer. And the timer would then go back here. Actually, no, the sequence would look like that. And this jump here would terminate loop. I'm thinking whether this snapping of objects maybe it could work for all objects. So here, when we have a hotkey object and it has a next connection to this flip, if I put it very close, it could kind of connect like that. And this macro recorder the same. So a sequence of objects which always execute in the same order, they would automatically create a stack. And the idea here is that they don't send any data through each other, they just schedule one after another. The number of connections would be far, far lower. I think we could also have some really nice audio effects here, like the sound that magnets do when they snap. It could be like, and when I move it out, it could literally unplug from the other object. So this is one option. This is something that would allow us to insert objects at the start and end. What if we want to insert them in the middle? Yeah, that's interesting. Okay, I think this is what we should do. We should have a general solution for stacking objects on top of each other. And they would create those lines. And this is where we will use our tapes. So if you remember, we had this idea of having this kind of tapes in our assembly environment. I don't know if we have any other pictures. Probably not here. Here maybe? No, I don't see them. Yeah, this is what we'll do. First, I think I will have to implement serialization for those objects. So let me do that. I will close this normally. And now I should not be able to restart it because the deserialization will fail. Unknown object type, instruction. Let's do simple registration. I don't want them to appear in the toolbar though. There is no point for having instruction, just generic instruction in the toolbar. Huh. Yeah, this is because we didn't serialize the state. Phi is probably some internal LVM opcode. I don't think there is a phi in x86. This is phi from Greek, like this is a Greek symbol, so there's no instruction like that. Okay. Okay. If I remember correctly, there were some crashes when I tried to move those instructions, but apparently not anymore. Nice. Okay, I guess we can remove this setup development scenario. Yeah, this useless card is here. We don't want it. Where do we fill this? Here, add object prototype. Seems we are just adding everything that's in the this names index. So the issue happens between those two files, between registering all of the prototypes here, which is used for deserialization and probably many other things. Actually no, mostly deserialization. And this, the code which populates toolbar. could add a new argument here. Is this going to compile still? I don't know if I can use enums in template arguments. Okay. Easy. And now we should be able to deserialize this. I mean, of course, I also have to honor this here. Okay, so we have this field here. I think we could rename this to toolbar prototypes. Simple rename. I think this should still work. Actually, no. I was thinking about moving these toolbar prototypes into this prototype library object. But no, this is a bad idea, because I remember our plan is to have multiple toolbars and to have toolbars for toolbars to be configurable. So actually it has to work more like except instead of prototypes, we'll have like a default toolbar. Now, let me think about the type of this pointer. So each object is part of 3 different collections now. Given that it's not going to be, it's just like the global prototypes, it's not going to be a lot of objects. But it feels weird to have them like everywhere. Anyway. Now the toolbar should not have a card, the instruction card widget, if we've done it right. Yep, it's not here. So here we have functions for serializing and deserializing state. Let's implement them for instruction. So each of our instruction is only going to hold this MC_inst. We are not going to hold address or size here. Address and size are actually going to be the properties that the assembler is going to track internally. Instruction is just instruction. It can have connections to other instructions, but it will only contain this MC_inst. I mean, maybe as optional properties we could hold those, but don't need them. Anyway. Actually, when we serialize, it would be nice if we serialized this not using LLVM internal those numbers because they don't mean much, but using names. I have no idea if we can deserialize this, so let's see. Can we do this in the opposite direction? Actually, there is no mapping from opcode names to numbers. Actually, I could use string view here to save some memory. This string map in LLVM, maybe it's a decent collection type.
Marek Kowalski says,
Hello. All the instructions implemented?
Yeah. We're good with instructions. So this is actually 3 of those. I was even looking how we could actually make this work. So we will have, so for instance, a program that will execute a loop will start with this instruction that will set the CX register to some value. And then we would have the loop instruction. This one, I think. Yeah. So from this, we will have a connection going here. And this card is going to have a connection on this side. So it's going to essentially call this timer in a loop. And the timer is going to be connected by just snapping it below the instruction. Right now I'm actually implementing something which is totally tangent to what I was planning for today. So I guess those, let's change them to green. instruction saving and loading. And I'm doing this the hard way because I want the JSON that AUTOMAT saves to be editable, like manually. So I'm trying to use human readable names. Instead of numbers, we will use strings. So LLVM has this nice class called string map. I am just going to use it. It looks perfect for what we need.
What's the use case for that?
Oh, this is just for executing macros in a loop. We will have other types of conditions. We will also have special instructions for checking the value of other objects. But right now this is the basic use case for assembler right now, to control other objects. This is why we kind of need it in AUTOMAT.
I mean manual editing, Johnson.
It's more of a matter of like principles, you know. I just think the way that software should work is to kind of allow people in the loop. So a user should be able to like inspect the saved file manually and like tweak some things if they want to. Or if you have some external script that will process this file, it should be as easy to do, as easy as possible to do. Essentially, like the point here is to not to just make something that's a visual language, but that's like a proper visual language. I'm looking at LLVM code and it's so good that I basically don't need to implement half of the collections myself. I can just use the stuff that LLVM has.
Sure. I understand, so JSON would also be formatted in file.
Yeah, I can actually show you how this looks. So the save file looks like that. Fairly simple. It contains the parameters of the window, where it's located, and a list of objects which are out there, including, for instance, timeline which has timestamps. It can be edited, and once you reload AUTOMAT, those changes will take effect. It would be nice to also publish some schema. I know there are some things like JSON schemas. We might do that, actually, eventually. It's not a priority. Yeah, so there's a hotkey object. It's configured to press F4 with those modifiers. And the next object has index 5, which is maybe not perfect, because this has to be kind of looked up manually by counting positions. We should probably fix that. Anyway. So we have our super efficient map. Nice. So this is how we serialize stuff. We call literally functions that emit JSON directly. This is super fast. There is no reason for this to be fast, but we do it like that, because why not? So now I should be able to...
It's so readable you could just write AUTOMAT rules in file. I like that. I wonder how its serialized assembly instructions look like.
We're going to see in a moment. So for example, this flip instruction, I can close AUTOMAT. Sorry, what?
I tried to compile AUTOMAT the other day on Macos 1, but gave up after some time. It might be hard to port for ARM.
We will do this. We will do this. And it's nice that you have a Mac. We will. I will use you as a test subject. I can also play with a Mac machine. I just haven't had time. It has so many bugs, even on like Windows and Linux, that I think porting this to Mac at this point in time, it wouldn't solve anything. It would just slow the development. Mac has all of the features that we need, so it's definitely possible to port AUTOMAT to Mac. It's just a matter of doing this. So I was at some conferences recently and I've seen how popular are Macs in the West. It's crazy. Yeah, we basically have to support Macs. Yeah, Silicon Valley, like half of the people use Macs.
Sure, I can be test subject. I stopped on Fastrigo Library because it's mostly optimized for x86.
Honestly, we almost don't use Fastrigo. Okay, I guess some of those may not be present. On ARM, yeah, I see that. Good to know, good to know. Okay, I see. We should start with a key. And then we can serialize our value. Okay, and this is it. This is our instruction. It has the opcode, which we are serializing as a string. We should probably also deserialize it. It will probably be deserialized as 5, yeah. Exactly.
I prefer Linux myself, but MacBook One machines are so performant that it's hard to compete. And unfortunately, SAE Linux, which is One Linux, is not there yet.
Interesting. My wife has a Mac and she loves the battery life. She told me about this. I wonder, is this really like M1 feature? And are like regular ARM laptops comparable, like this kind of stuff? Okay, we have to follow a fairly rigid structure.
Hard to tell. It's also a case of build quality of laptop battery life, retina screen, etc. It's just good hardware. Software, not so much, but it's at least Unix-based, so tooling for dev is good.
Yeah, I did use Mac for some time. Eventually I got annoyed by the command button. It's different for the sake of being different. Which honestly triggers me.
Yeah, but you can get used to it. One also has x86 translation layer called Rosetta, so it can run x86 program. Maybe I'll try to leverage that for AUTOMAT compilation.
Interesting, yeah. So I remember there was a library by Intel for running x86 on ARM. Android devices, all of them used to have this. None of those. Actually, compilers should know. Houdini, exactly. Oh, sorry, it's the other way. It's for running ARM on x86.
I wonder if Android emulators using that.
Androids in general are using that. So Android has different it supports a lot of architectures. There used to be MIPS and MIPS 64. There is obviously ARM with the 32 and 64-bit versions. There is x86. x86 I actually am not sure if it supports the 32-bit version. So those are some of the instruction sets that Android supports. And the thing is, people who write apps are only required to include machine code for ARM32. At least that used to be the case. Now they are required to include the machine code for ARM64 and all of the other architectures. If they want to run Android, they have to emulate ARM64. So ARM64 is the native architecture for Android. Even if you're writing a port of Android for a different architecture, it has to support ARM. Otherwise, it will not pass Google's certification. And it will just not be able to run most of the apps. Okay, so we have an opcode name. Now let's look it up.
In case of portability, you thought about Flutter?
I'm familiar with this. Flutter is Flutter a native thing? Nope. So Flutter kind of comes packed with Dart. Dart isn't bad by itself, but it locks you out of many things. I mean, it has FFI, so theoretically it's equivalent, but in practice it's just not the same as C++. I wanted to see what happens when I don't find the key. Okay, it just returns end. I'm also thinking about error recovery here, so if you change something in the JSON, I want to print proper error message. But I don't think recovery is possible here. If the opcode name is broken, then yeah, it's just an error. Okay, now it should be possible to deserialize our instruction, at least the basic one, without any arguments. Let's take this one. Are there any instructions without arguments? Yeah, there are, like this one. So now I can close it. And there we go. It was deserialized. Now,
Referring to JSON schema, there are many tools for generating schema from regular JSON.
okay, it's not exactly perfect. I mean, of course, like automated tool, it's not going to infer the, for example, repeated fields. Yeah, I think we will generate this schema, but we'll do this properly, our way. So the thing is, we have
Yeah, the sample should also be complete.
so maybe we can change how we store the objects so that it fits better with a JSON schema model. But generally the values that are permitted here, the value especially, it depends on this type. Anyway, now it's time for operands. If there are any operands, then yes. Actually, we don't need this. Yeah, we can iterate like that. Okay, sorry. We have to do it like that.
Back in the days, I've implemented web form generator from JSON schema. It mostly can handle all strange cases, so it's not needed to design. For JSON schema, you shouldn't worry about that.
Yeah, I mean, once we have JSON schema, we could implement like all sorts of things out of this, because JSON schema has more rich information than JSON itself, especially about the like permitted values, for instance. Or like I don't know if JSON schema can encode this information between fields. Like I just showed in our state we have this type which defines the type of a value. So some objects can store the value as a simple boolean, but some other objects like hotkey, they actually store it like that. We could just move this here from hotkey into the... So instead of type, we would have just a field with some name, and that name would be the type of the object. Also, the JSON that we are writing here, it's not 100% JSON because it cares about the order of fields. When we are parsing it, we need to know the type before we can parse the value, this kind of stuff. So it's...
Knight says,
Hey everyone.
Hey, Knight. The presentation from Causal Islands is out. So There it is.
Function.
Marek Kowalski says,
Sky is the limit in this case. Also, when you would have schema, you could just put that schema into VS Code and have auto-completion for fields.
Knight says,
Nice. That will...
I think I should like this.
So now I have a planet that snaps. And this is the point.
Okay, I could store all of the operands as just an unsigned numbers, but I think that might be a little...
Let me go leave a comment.
Nice. I think it makes sense if we encode operands in a slightly more readable way. Oh crap, I didn't want to change that. Yeah.
Marek Kowalski says,
Gotta go. Happy hacking.
Yeah, see you around.
Coon P says,
New music.
There is a little bit of new music. I can actually skip the old ones. It's always to have that. This is the new part. It's just a couple of tracks. And they are super trumpet heavy, so brace yourself. I basically told the AI to generate just crazy trumpet solos and picked a few of them. Okay, we are actually only supporting two types. Of operands. Unknown ones are just null. We have immediates and registers. A condition code is also treated as an immediate. By the way, let me check if we serialize them properly. So let's create some instructions. This I will delete. Say I want to set the CL to something, and then I want to create my loop. This is for looping. Those objects I don't need, I will delete them.
I was just playing metal in other tab.
Okay. So here are our instructions, and we are properly serializing register names. Cool. Now deserialize.
Knight says,
If someone asked me what math's area of expertise or greatest passion is, I would say animations. Am I right? White?
Yeah, probably. Yeah, I actually don't know myself. I think I'm... In terms of my interests, I think I'm kind of similar to most of the people who go to technical studies. Maybe not quite animations, maybe user interfaces. Oh yeah, maybe this is a better category.
From what I can see, animations really stand out in everything you touch. I noticed this in your talk in Berlin as well.
Yeah, I just wanted to illustrate some of the examples. So each slide is, like, not each slide, but a lot of the slides are animated. Actually, we can do it differently. So when we are parsing operands, we know what is the opcode. So I'm afraid we have to create another string map. That's fine. Easy. So now we have to check the map. Okay, and if we mess up here, can replace it with a generic register. I don't need this is string, luckily. But I need to get 64-bit integers. Cool. So we did recover some of those values. Now we can actually see if editing the JSON works. So I will open AUTOMAT state and try to change the immediate value. I want to set this to 10. Yep, it now has value 10. I could theoretically serialize this in a shorter version. I could just serialize an array, which would always contain the opcode name first, and then a sequence of operands. It's doable, but I think this will be more readable. Okay. So we can now store the cards. I think now we should add the next connections. Actually, this snapping thing, I think we should implement this, but this is just going to be a nicer way to connect objects together. Yeah. So if the point where connection starts is very close to the point where the connection ends, and I'm holding one of those objects, it could snap in place and hide the connection. And when it's far enough, it will show the connection as a cable. Cool. I will do a short break. 5 minutes or 10 minutes to refill the tea. Actually, I don't know how long tea making takes. But then we will add the cables to the cards. It's not perfect, it's not what we wanted, but I think cables are a nice way to temporarily just connect those cards somehow. So, be right back. was about 6 minutes. Okay, our instructions need cables. How do we do this? Okay, so we have an args function that we have to implement. I'm starting to remember this. Okay, we have it here. Okay. It includes a pointer to assembler. Actually, no, we don't want this kind of argument. I think it should be the opposite. The assembler should have pointers to instructions. No, let's get rid of this. There's going to be no instruction like that. I am leaving this code for now because we will try, at least we will try to use it later. Next week we are going to write the assembler. So this week was for instruction, next week we are writing assembler. Find or create assembler. We can comment this out as well. I'm just temporarily disabling unused code. So each instruction should have a pointer to the next argument. And that should be enough to draw the arrow below the instruction. Like the cable below instruction. Can also try to make a simple loop. So let's run this. Yeah. Of course, our run function isn't actually running the machine code, so we should fix that. But we'll do this next week. This week, I think we should still have this side connection here on this side. Actually, this is how a loop will look like. Or maybe even that, like that. And now we have an example program in AUTOMAT, which is supposed to run. Actually, it will run forever because we are not actually running this code, but this is an example of how assembly will be used in AUTOMAT, essentially. Here we have a card which will set the value of some register to 10. A register will be displayed in the assembler object. Okay, now some instructions have the side connections. We should show them. This will actually be a new argument type. Yeah, it's fairly simple. Okay, and here there might be a flag that will allow us to decide if it's a jump. For example, this if is branch. Okay, so here we have the other connection. We could style it now. So I would like this conditional jumps to kind of be located on the side. Let me actually see. Is this a branch? Yep. This one is also a branch. Oh, I see. Argument should be a virtual class. Let's change the icon. Okay, this is a mixing class. Sure, looks good. What icon could we use for jumps? This is a nice one. We can do something like that. And I have an idea to clear all. Regarding scale, I think we could put ourselves in this 4x4 rectangle around center. What is this? Okay, we actually have to make it like that. think this leg should be horizontal at the end. Like that. Maybe it's too thick. So this is our dude. It's too large. We will have to scale him down. Let's try that. And the scale is probably going to be wrong here. I want to have millimeters here. And there is our diode, but it looks decent. It just could be larger. And there it is. Now this argument, it should come out from a different position on the card. I would like it to go from the right side of the card. How do we do that? Here. Arg start. I think we should fold most of this code. Okay. So for jump argument, we will return our custom position, custom direction. We could even position this argument, this start, on top of the card. So it could literally jump. It could literally come from here. So in the case of our loop, this jump is actually not necessary. We are just not going to connect anything here, because we just want to terminate after 10 iterations. Okay, I think this leg is too thick. Let me change that. I think the stuff that we have is pretty sufficient already. Could think about snapping now, but I will have to leave early, so I'm not sure if I will be able to finish the snapping today. And I don't want to leave the code broken over the weekend, so that on Monday we have a working build. So even though this jump is not connected anywhere, our assembler will actually go over all instructions, and for each instruction that jumps that doesn't have a connected jump, we will insert an exit point, kind of. So that leaving the assembler through this exit point will cause this cable to light up. I wonder what would be the equivalent instruction if we didn't have CX to use. Let's see. Let's say we want to use DX. We would set this to 10 or whatever. Run a timer. Then we would decrement DX. Could define it like that. So if it's not equal to 0, then this jump would go to start. So this is also, yeah, this is j not equal 0. I mean, actually not j any 0. This 0 is actually the address where we want to jump. This isn't obvious what it does. So this way, by manually editing those conditions here, we can see other options, like free. What is free? This is greater equal. This one actually goes out of bounds. There are a couple different jump instructions. So here is one which has just 1 byte offset, and this is the 4-byte version. This one is obviously much more powerful. With this we could jump almost anywhere. I think regarding the jump instruction, because it has variants that kind of have to be switched to accommodate the distance. We might just as well have just one card and the assembler will kind of dynamically switch this variant based on what we need. This is not possible for loop though. Loop only has 1 bit offset. Loop can only be used for very short jumps. So when we convert this to assembly, we will have 3 exit points. There will be one here, which will have to transition from assembly to automat. One here and one here. Okay, so this was one loop. Let me try another, like yet third approach for writing loops. Let's now do, for example, AX. We will start by clearing it. Then we will execute some AUTOMAT object. Then we will let's also set up the maybe counter. Or not. We also need to increment AX. So those are three ways to write a loop. One, we can use the CX register, because CX register has some dedicated instructions for looping. It's probably the shortest way. Definitely the shortest way. And then we can use a general purpose register like DX to count down. Or we can count up and use comparison instructions. Yeah, to decide when to finish. And this block of instructions would actually execute sequentially. So it's not going to be like, hey, I'm executing this, then this, then this. They will be loaded in memory one after the other. We will jump to the first one, execute them until the end, and this exit point, this jump connection, will be intercepted by some special exit point and will trigger the next object. Yep. I think that looks cool. I will think about connecting objects on a tape. This will be nice. If we can introduce those chains of sequentially executed objects. Okay, I guess this is it for today. Yeah, it's Friday, sure, so the stream is shorter. I didn't implement the stuff that I wanted to implement. We have saving and loading, we have pulling out. We don't have so this is not going to be an instruction specific thingy. Now I just want to just implement tape-based sequences of objects. But this now that it's going to be more general, right? So if this is going to be usable for like even regular objects like those. So when two objects are touched like that, they will summon a tape. So behind them there will be just a piece of paper, but not just regular flat paper. It will be this like flexible paper that will appear. And they will behave slightly differently then.
Marek Kowalski says,
In the future, it would be cool to have some templates groups of objects, like template of loop counter or something.
Yeah. And sometimes it would be nice to kind of lock like a really complex collection of objects into a higher level object. Yeah, totally. I think because tapes are more kind of general, then they are going to cover not only assembly instructions but all types of objects. Because they are more general, we should really think about them. and maybe not implement them in a single day, but more like a month, so that we have like nice interaction for like taking objects out of a tape, inserting objects in the middle of the tape. Yeah, like a proper widget with all potential things that you imagine should be possible. They should just work. It should be like a properly supported primitive in the UI. So I will leave this for later, but I like this so much that I will turn this into a large project, one of those that we have here.
That would be cool. Tape is core of AUTOMAT.
So, some time ago I've seen trailers for GTA. And so the idea for the tape, it actually comes from Monty Python. At least this is, I mean, of course it existed all over the place, but Monty Python used this a lot. Here's an example. This is a wavy line. I haven't seen anybody in computer graphics implement this kind of effect. So it's definitely going to be interesting, and numerically it's not that complex actually, this shape. If we position control points at the top and bottom of each of those sections, then we can model this as a single Bezier curve. Or not necessarily Bezier, we can also do a segment of a circle here. But Bezier I think would be nice. So those would be Bezier segments, and the lines between the two segments. I think there is a way to convert this into a Bezier patch. So we will just render a sequence of Bezier patches, which are very fast to render actually. We can do them mostly on the GPU. We just provide control points, and the GPU takes care of tessellation, shading, everything. We could even do this kind of line-based shading if we want to, because we can write our own shaders. So it's going to be very, very interesting. And I've seen in a GTA trailer, okay, it's muted, at the end, it actually shows a nice effect of a banderole of this tape flying in. So if I play it very slowly, I will do this frame by frame, actually. I can play it? Why? What's up?
Lot of cool stuff to work on.
Yeah, we have to pick our battles now. Okay. So here is the tape flying out. It was animated mostly manually, but I think I've seen... No, this was just a manual animation. So somebody just drew all of those frames. But we can do the same thing procedurally. Our tape is going to be oriented differently, so it's not going to be viewed from the bottom. The idea is similar though. Okay, so with all of this, I guess we can say that instruction library and instruction widget are complete. I mean, not 100% complete. It's never going to be %100% complete, but it's functional enough that we can start working on the assembler. So next week, I expect we will spend working on this new type of object. So we will first have to kind of have the assembler object, but we broke it. Because we did some changes in the instruction, but we will fix it. Cool. So that's the plan. So the assembly environment is actually coming close to an end. This project. Next 2 weeks we should be finished. Cool. Okay, so that's it for today. See you on Monday next week. Bye.